I want to ask you one question. Don't answer it yet. Just sit with it for a second. What happens step by step from the moment you run kubectl apply -f deployment.yaml to the moment your container is actually running on a node and serving the traffic? If you hesitate, if you know roughly what happens, but you couldn't trace the exact sequence, every component, every handoff, and then this episode is going to change how your next Kubernetes interview goes. Here is why I open with that. I have sat on the another side of the table for hundreds of Kubernetes interviews, and I can tell you what almost everyone does. They describe step one, I run, apply, and step eight, the pod is running, and nothing in between. The whole cluster, the API server, etcd, controllers, schedulers, and the kubelet, that entire machine that actually does the work. The engineer who gets the offer are the ones who walk me through in middle every step, because the middle is where Kubernetes actually is. So that's we are building today, not a cheat sheet you memorize and forget. A mental model, the kind that survives the follow-up questions, whiteboard sessions, and that weird scenarios your interviewer invented 20 minutes before you walk. Whether you are a fresh graduate walking into your first Kubernetes interview, or you have run cluster for a year, you're going for an architecture role. By end of this, you will be able to trace that path in your sleep and back it up with the real production stories. Welcome to episode 4, Inside the Interview Room, Kubernetes Masterclass. Let's get inside. Let's start where every interview starts. What is Kubernetes? You will see it written as K. The 8 just standing in for 8 liters between K and E. It's an open source container orchestration platform. It came out of Google and it was donated to the CNC, the Cloud Native Computing Foundation, back in 2014. Under the hood, it's based on Google's internal system called BOG, which was scheduling billions of containers a week at Google scale, long before any of us had heard the word pod. Now, the honest question a fresher always wants to ask but doesn't: why do we need this thing? So, let me make it concrete. L- Look at two pictures on screen. One on the left side, uh, without Kubernetes, you have got containers scattered across bunch of servers, wired together by hand, running one or two containers like that. Totally fine. You can babysit those, but the moment you're running hundreds or thousand across dozens of machines, scheduling them onto the right servers, restarting the ones that crashes at 3 a.m., exposing them on the network, rolling out new version without taking the site down, scaling up when Black Friday traffic hits. Now you need something to run that for you. That something is Kubernetes on the right, same containers but organized, grouped, labeled, and here is the part I want you actually memorize, because it's backbone of every answer you will give you today. 5 things Kubernetes does. If you can articulate this 5, you can reason your way through almost any question at any level. 1. Container scheduling. It places containers on nodes based on what resources are free and what constraints you have. 2. Self-healing. It restarts failing containers. It replaces pod on node that dies. It kills the pod that fail their health check. 3. Service discovery and load balancing. It gives a group of pods a stable DNS name and IPs so things can find each other. 4. automated rollouts and rollbacks. It updates your app with strategy you choose and roll back automatically if the new version is bad. 5. Storage orchestration. It provisions persistent storage on demand from cloud provider, NFS, or local disk. Schedule, heal, discover, update, store. Every Kubernetes interview question you will ever get is really just one of these 5 wearing a different question. The word change, the concept fundamental is always okay. This slide is the one that separates people. If you take nothing else from this episode, it's Kubernetes cluster, Kubernetes architecture. Kubernetes cluster has two planes, control plane and worker node. Control plane, that's the brain of your cluster, and worker nodes, that's the muscle of your. The brain decide what should happen. The muscle actually runs on your container. In real production cluster, the control plane runs on its own dedicated nodes, kept separate from your application workload. So a busy app can never starve the brain. Let's walk the brain first. Control plane. Components by component. I'll tell you what each one is for, not just its name, because for is what the interviewer is listening. Cube API server. This is the front door, entire cluster, every single request. You're running kubectl, a controller doing its job, kubelet checking in, all of it goes through the API server. It validates what you send, checks whether you are allowed to do it, and it's the only thing that talks to etcd. If you remember one component, remember this is the front door. etcd, this is distributed key value store, and it holds all cluster state, every object, every config, the entire desired state of your world lives in the etcd. Here is the line that lands in interviews. If etcd goes down and you have no backup, your cluster memory is gone. That's why we back it up religiously, and we'll come back to that in a real incident later. Cube scheduler, when a new pod needs a home, scheduler is what looks at every node and decide which one it should run based on free CPU, free memory, or affinity rules on tenths. It doesn't run the pod, it just makes the placement decisions and writes it down. Kube controller manager, this one runs controller, and controller are the soul of Kubernetes. A controller is loop that constantly compares what you ask for against what actually running and works to close the gap. You said 3 replicas, only 2 are live. The controller notices and creates the third one. That reconciliation loop is the single most idea in the whole system. Cloud controller manager. This is the piece that talks to your cloud provider like AWS, Azure, GCP to wire up load balancers, attach volumes, register nodes. It's the bridge between Kubernetes and cloud underneath. Now the muscle, the worker node. Every worker node, whether you have 3 or 300 or 3000, runs the same thing. Kubelet, the node agent, it watches the API server for pods that got assigned to its node, and it makes sure that those containers are actually running and healthy. The kubelet is the control planes hands on each machine. Kube proxy, this maintains the network rule on the node so that service load balancing works. So traffic hitting a service actually finds its way to healthy pod behind. And the container runtime. Containerd, CRIO, or Docker in older setup. That's the thing that actually pulls the image and runs the container. Kubelet doesn't run container itself, it tells the runtime too. two more strips at bottom. I'll keep this tight because we have got whole section on them. On the network side, CNI plugin. CNI plugin gives every pod its IP, wires up pod to pod networking. Service gives the stable access, cluster IP, node port, load balancer. The ingress controller does layer 7 HTTP routing, and core DNS is the cluster DNS. On the storage side, persistent volume are actual cluster storage, and the persistent volume claims are how pod says, I like some of that, please. Here is how I want you to hold on all of this. Kubernetes is declarative. You declare the state, you it's self-healing, it recovers on its own. It's scalable, built for it, and it's extensible. There is an ecosystem of add-ons. Declare it, it heals, it scales, it extends. If a junior candidate can name these components, that's a pass. If you can explain how they talk to each other, you are the one getting the call back. Now we pay off the hook. This is the answer to the question I opened with. 9 steps from the moment you hit enter to the moment your container is running. I'm going to test all 9 and I want you to test them with me because this is walkthrough that gets the offer. Step 1, you run kubectl apply -f deployment.yam. You have declared what you want. That's all you did. You stated intent. Step 2, the request hits the kube API server. The API server authenticates you. Who are you? Then authorizes you with the RBAC. Uh, are you allowed to do this? And then runs admission controller, which can validate or even mutate your request. Only if all of that passes does it move on. Step 3, the API server writes your deployment object into HCD. It's now persisted. The cluster officially knows you want this. Notice nothing is running yet. We have only recorded desired state. Step 4, the deployment controller. Inside the controller manager, it watching, it sees a new deployment with no replica set. So it creates the replica. Step 5, the replica set controller now sees a replica set that wants, say, 3 pods and 0 x. So it creates pod objects, 3 of them, but hold on. These pods have no home yet. They are unscheduled. They exist on paper. Step 6, the scheduler wakes up. It sees the pod with no node assigned. It looks at every node, free CPU, memory, affinity, taints, picks the best fit and assign the pod by setting pick that node name. That's the placement decision. Step 7, the kubelet on that chosen node is watching the API server and it sees a pod has been assigned to me. Now the work comes down to the master. Step 8, kubelet tells the container runtime to pull the image and start the container. This is the step most people jump straight and skip everything before it. Step 9, the kubelet reports status back up to the API server. The container is healthy, the pod is running, and now, only now, your app is live. That's the whole path, and here is what I need you to internalize. Every single action you take in Kubernetes follows this. You declare intent, API server gets it, etcd records it, a controller reconciles it, and the scheduler places it. The kubelet make it real. Deployment, jobs, scaling, updates, same skeleton every time. Want to prove it to yourself on a real cluster? 3 commands on the slide. Run kubectl apply -f deployment.yaml, then kubectl get events where you can see the event and Watch, you will literally see scheduling, then pulling, the pulled, then created, then started, scroll by in order. Then kubectl get pod -o void to see which node it landed on. Most candidates stop at step 1 and step 8. Don't be that candidate. Know it, visualize it, explain it, every one of 9. Kubernetes gives you a menu of workload types, and choosing the right one is the real production decision, not trivial. Let me go left to right. For each one, I'll give you the freshest one liner and when do I actually use this. That's the senior need. What's the smallest deployment unit? One or more containers that shares a network and storage. Here is the thing freshers get wrong. You almost never create a bare pod and you run kubectl run for a quick test and that's about it. Real workloads are wrapped in something smart. Replica sets it ensures n copies of pods are always running and self heals kill one, it makes another, but you rarely touch the replica sets directly either. Deployments, this is your workhorse. Deployment manages replica sets for you and gives you rolling updates and the rollback. It's the right answer for anything statelets, web servers, APIs, workers, where any pod is interchangeable and you can replace them in any order. StatefulSet, this is stateful app. It gives each pod a stable identity, predictable names like myapp0, myapp1, ordered startup and shutdowns, and stable per pod. This is what you reach for when identity and order actually matter. In case of databases, Kafka, Zookeeper. Daemon set this runs exactly one pod on every node or every node you select. It's for node level service, long agent, a monitoring agent, a network plugin. New node joins the cluster, daemon set pod shows up there automatically. Job and cron. A job runs a task completion, a database migration, a batch process, and then stop. A cron job is a just job on schedule like Kubernetes native cron job. Now, here is the mental shortcut on the slide, and it's how I actually decide. Ask 4 questions: is it a one-off task that must finish job or cron? Does it need stable identity and its own storage? StatefulSet, does it need to run on every node? Demonstrate, is it stateless app that just needs updates and rollback? Deployment, and if you are just testing something quickly, bare pod and only. Freshers memorize what each object is. Seniors knows when not to use each one. Knowing that you should never put a database in plain deployment is worth more than reciting all 6 definitions. Next up, networking. This is where a lot of otherwise strong candidates falls apart because they have never had to think below the service. We'll cover how pods gets their IPs, how service load balances, how ingress does the layer 7 HTTP routing, how core DNS lets a thing find each other by name, and what the CNI plugin actually does at the packet level. Hold that thought. The packet is path is the question 7 and it's favorite of mine. So service types. Service provides stable endpoints for pods. The cluster IP, internal only, stable virtual IP access within the cluster and for the internal traffic. A node port that exposes service on the every node at the static port, that's a range between 30,000 to 32676. It can be used for dev environments or on-premise environment. Load balancer provisions a cloud load balancer, extends node port, good for single service exposure on the cloud. And external name lies on the external service, not the proxy. Ingress, it manages the external HTTP and HTTPS routing to the service, requires an ingress controller like Nginx, traffic, or the tailbase. It does the host-based routing, path-based routing, TLS termination, and authentication, and other features. So basically, external client hits the URL, it goes to your load balancer, cloud load balancer. Then load balancer passes that request to the ingress controller. Ingress controller actually routes the traffic through the service to the end of your pod. Again, ingress is not a service type, it's a routing layer above the services. The third one is the DNS, service discovery. Every service gets the DNS entry. Service name dot namespace dot spc dot cluster dot local. Whenever you want to access any service, you can use this DNS, and this DNS is handled by the core DNS. Core DNS handles all DNS resolutions within the cluster. DNS is the primary way applications discover the services. Pod look up the DNS in the core DNS. Core DNS resolves that through the cluster IP. So traffic flows from user to internet, internet to the load balancer to your ingress controller to your service to your pod. This is the path and some of the useful commands. The storage, because containers are ephemeral, but your data can't be. The key trio, a persistent volume claim, and the storage class. Persistent volume is actual storage in the cluster. It is provisioned by admin or dynamically by storage class. The examples: AWS EBS, Azure Disk, NFS, local volumes. Then persistent volume claim, the user's request for storage. It is the pod asking for slice of it. It binds to the matching PV. Pod mounts the PVC, not the PV. Example request: when you ask for the 10 gig of storage or the uh, PV writes, read write once. The next is storage class. Storage class is what lets Kubernetes provision that storage dynamically on demand from your cloud. It automatically creates a preview when PVC is created. Provisioners can be AWS, EBS, CSI. So access mode: read write once, read write by a single node, read only read only by many nodes, and read write many, read write by many nodes. What are the reclaim policies? Delete PV and underlying storage deleted when PVC is deleted. Retain PV remains after PVC deletion for manual recovery. And recycle, this is the deprecated and we do not use it. Some of the useful commands that you can use to define the storage, define the persistent volume, PVC, and storage. The security in Kubernetes. In real cluster, this is not optional, it's a foundation. So RBAC, service account, secrets, and network policies. So RBACs that controls who can do what in the cluster. So it has roles where namespace scope, permissions, cluster roles, cluster wide permissions, role bindings, assign roles to a subject in a namespace. Cluster role binding assigns cluster role cluster. So what are the subject? Users, certificate based collection of users, that's a group, service account, identity for pods, token mounted automatically. Principle of least privilege. I ask this almost in every interview. What is the principle of least privilege? Grant only the minimum permissions required. Secret management, store sensitive data like password, tokens, certificates, so where you can store that into the HCD. Secrets are base 64 encoded by default, not the encrypted. So, what are the best practices to store the secrets? Enable encryption at rest. Use external secret vaults, secret managers like vaults, AWS secret managers, etc. Use sealed secrets, external secrets operator for GitOps. Never commit secrets manifest to the Git. I have made the separate video, that's a Git masterclass, you can watch it for. Base 64 is not a security, it's just the encoding. Network policy, it controls pod to pod traffic at the network layer. How the pod to pod communication will happen through the network policies. Without network policies, all pods can talk to all pods. So where this is the default behavior of Kubernetes. With network policy, allow only the required traffic and deny by default. This is the principle of least privilege and deny by default. Requires CNI supports to define the network policies. So CNIs are Calico, Callium, and Planner. Some of the useful commands: security checklist, use dedicated service account for workloads, follow least privilege principle, enable HCD encryption at rest, use external secret management, apply network policies for micro segmentation. Administration in Kubernetes. This is again the one of the important topic that we discuss in the interview. Administration like scaling, updates, upgrades, and back. What is scaling? Scaling is like horizontal pod auto scaling. So it scales pods based on the CPU, memory, or custom metrics. VPA automatically adjusts resource request and limits. Cluster autoscaler or carpenter adds or removes nodes when pod cannot schedule. Standard stack, HPA plus CA or carpenter. So updates, a rolling update incrementally replace old pods with the new pods. The question that I usually ask, if your rolling update is stuck somewhere, old pods are not getting deleted, but new pods are provisioned. So that is also one of the important topics. So recreate kills all old pods, then starts new. Blue green, two full deployments, switch traffic via service from blue to green. Canary deployment sends small percentage of traffic to new version. Cluster upgrades. Also, I usually ask in the multiple interviews how we can do the skip level cluster upgrade. So how we can do that? Upgrade the control plane first, and drain the nodes, upgrade the nodes, and uncordon and resume the traffic. What is the backup strategy? You always back up your HCD core of disaster recovery. Use HCD CTL snapshot, store of cluster, or Velero backup, application level backup, PV, namespaces, resources. This does not replaces your HCD backup. Test, restore quarterly, and untest backup is not a back. Key takeaways: scale with HPA autoscaler, a rolling update for zero downtimes, upgrade one minor version at a time, backup HCD regularly, automate, test, and document everything. Now let's move to the interesting thing, which we are here and we want to see that 10 interview questions and answers. So here I'm gonna show you three beginner questions, three intermediate questions, two advanced, and two scenarios. Question number one, this is the beginner level question. What is Kubernetes pod? And almost in every interview, this has been asked. But my favorite is second part. Why would you ever run more than one container in a pod? So what is the expected answer? The pod is smallest deployable unit in Kubernetes, one or more containers that shares network namespace, IP addresses, and optionally storage volumes. All containers in pod communicate via localhost and see the same network. Why we keep the multiple containers in the one pod? Multiple containers in a pod makes sense for the sidecar pattern, a primary application container plus an helper. So where you add the main container and the sidecar container, shared network namespace, IPs, localhost, shared volumes, and this is optional. Common sidecar use cases: service mesh proxy, Envoy Istio injected automatically, a log shipping sidecar, a reads app log for shared volumes and ships to Elastic. Configuration reloader watches config map and changes signals the main app. And init containers run to completion before main containers start. Used for DB migrations, waiting for dependencies, configure the environments before running the actual applications. What are the hiring managers' expectation? Beginner candidate knows a pod runs container. I am testing whether they know why multi-container pod exists. The sidecar pattern, knowing init containers is a strong junior to mid differentiator. Why we use the sidecar pattern? What are the common mistakes? A pod is likely Docker container. A pod is an abstraction above the containers. A pod can contain multiple containers. Fitting pod is equal to container shows unfamiliarity with the Kubernetes fundamental. So this is smooth. So let's see by the production example in e-commerce system. What is a pod? This is the online shopping platform, store front end, checkout payment service, inventory stock service, and the database MySQL. So where what is pod? Pod is a smallest unit in Kubernetes. It can have one or more containers that work. For example, checkout service pod, main container, checkout app, plus sidecar container for log collection, log collector. Shared network, both containers share the same IP address, localhost. Work together, containers in a pod communicate using the localhost and share resources. Shared storage, they can share volumes if needed. Real life in e-commerce, user places an order, store sends the request, checkout pod, payment is processed, order is confirmed. So why use multiple containers in pod? Example, log collector sidecar can collect logs from the main app without affecting the application. Key takeaway, pod is like a single unit on the server. It helps run your application and its helper containers together. Follow-up questions. There are 5 follow-up questions that you can refer, and it's short answer. So mostly these questions are asked in every Kubernetes interview on the pods and containers. Question number 2, again, it's a beginner level question. What is the difference between deployment and stateful set? Most of the interviews, this question has been asked. Okay, so deployment is for stateless applications. Stateful set is for stateful applications. Let's see the deployment. What is the expected answer? You need to provide what is the deployment and in what scenario you are using the deployment and the stateful set. Pods are interchangeable. Any pod can be killed and replaced without impact. Pods get the random names, my app, ABC123, like that. No stable storage per pod. Rolling update replace pods in any order. It can be used for web servers, API services, workers. Where in StatefulSet, pods get ordered predictable names, myaf0, myaf1, myaf2, so on. Each pod gets its own persistent volume claim that persists through the pod restart. Pods start and stop in order. So, like my app 0 will get started, stopped first before the my app 1. A headless service cluster-none provides DNS entries per pod, like myapp0.myapp.namespace svc.cluster.local. Where we can use it can be used for the databases, MySQL, Postgres, Mongo, etc., etc. Kafka, Elasticsearch, Zookeeper, any application where identity, order, or pre-instance storage matter. What I'm expecting as a hiring manager, I want to hear headless service and per pod PVC. If candidate only says StatefulSet is for databases, candidate have theoretical knowledge. Knowing the headless service DNS pattern is hands-on. What are the common mistakes or common answers that common wrong answers that candidate provide always? StatefulSet is for apps that needs persistent storage. Incorrect. A deployment can mount PVC2. What makes the StatefulSet unique is stable identity, ordered operations per pod PVC, not simply persistent storage. Let's see it by real production scenario, e-commerce. So same scenario where store, front end, checkout, payment service, inventory stock service, and your database. So what can be the deployment? What can be the stateful set? So example, your front end service, multiple copies run same app, any pod can be replaced anytime. One service, multiple. In case of stateful sets, for example, it can be run for the database MySQL. Each pod has its own identity and its own storage. For example, headless service cluster IP equals to none. It can provision MySQL 0, MySQL 1, MySQL 2, like that, and each one can have its own PVC. Deployments are easy to scale up, scale down. Pods are replaceable, perfect for web servers, APIs, or workers. Where StatefulSet provides this stable network identity, own persistent storage, and in the order start stop of pod. Frontend can go up and down anytime without impact, but database needs stable identity and storage to keep your orders. Follow-up questions. These are the 5 follow-up questions that you can provide the short answer, which is available question and answer. So mostly these questions are asked as the follow-up for the PVC storage class. And question number 3: what is the RBAC in Kubernetes and how does it? So this is again most important part of the Kubernetes interview. What is the expected answer? RBAC controls who can do what in which Kubernetes. Role defines permissions, get, list, create, delete on resources, pods, deployment secrets within a namespace. If you want to define the cluster level role, just define the cluster. Same but cluster wide for or cluster scope resources like namespaces and role binding. Bind a role to subject, user, group, service account in a namespace. If you want to bind a role at the cluster level, then you can use the cluster role binding. It binds a cluster role cluster. What are the subject? Users, human users identified by certificate, CNs, or OIDC token. A group's collection of users, service account, identities for pods, and principle of list privilege. every subject gets the minimum permission required. Audit with kubectl auth can -I. What is the expectation by the hiring manager? Distinguishing a role versus cluster role versus two binding types is the minimum. Mentioning service account as pod entities and principle of least privilege signals security awareness beyond the textbook RBAC. The common mistakes are usually candidates provide the answer RBAC is configured in the config file, Kubernetes handles authentication, who you are. RBAC handles authorization, what you can do. Confusing with the authentication and authorization is a fundamental security crack. You have to focus. What is the production example? Right people, right access, right. Same example. Store front end, order service, inventory stock service, admin, black. What are the roles? Developers, order service, support, the platform admin. What they can do via RBAC and the resource in the scope. Developer can manage their own app in development environment. Deploy, update, view log. Namespace, dev. Not in the other namespaces, only for their app. Order service can access only what it needs. Get order, update orders, status. Resource orders only in the prod namespace. Support read-only access for troubleshooting, view pods, view logs. Again, this is the team, support team can have access, read-only access in the production. And platform admin, it has full control of cluster operations, all resources, all namespaces, cluster-wide access, all the resources. How it works? Define the permission, role, cluster role, bind to user, groups, service accounts, role binding, cluster role binding. Kubernetes API server checks the access, allows only if permitted. Real world impact, secure by default, least privilege. Service can access what they don't need. Easy to audit, who can do what. RBAC, make sure every user, service, and tool gets only the access they need, nothing more, nothing. What are the follow-up questions? You can see the follow-up questions and the short answer that you can use in your in question number 4. How do liveliness and readiness probe work, and what happens when each one? What is the expected answer? You have to explain what is the liveliness probe, what is the readiness probe, and the liveliness probe. It checks, is this container still healthy enough to keep running. If liveliness fails after failure threshold time, kubelet kills and restart the containers. Used for deadlocks, infinite loops, uncoverable states. Readiness probe checks, is this container ready to receive the traffic? If readiness fails, pod is removed from service endpoint, traffic stop, but container is not restart. You have to focus. It is used for startup warm up, maintenance mode, or dependency unavailable. Startup probe for slow starting applications. Disable liveliness readiness until it passes, because if some application needs some configuration, some environment setup that can be used with the that can be set up or warm up with the startup prop. Prop types: HTTP GET, response 200 to 399, TCP socket connection accepted, exec command exit with 0. What is the hiring manager's expectation? The key difference: liveliness failure kills and restarts the container. Readiness failure only removes the pod from endpoint. Container keeps running. Knowing the startup prop for slow app is the strong senior level addition. What are the common mistakes? If readiness fails, the container restart. No. Readiness failure only removes from the service endpoint. Container keeps running. Restarting would cause cascading restarts for every temporary dependency issue. So you have to always set sensible initial delay seconds, period seconds, timeout seconds, and failure threshold. You should not mix all these three probes with each other. Liveliness has the separate purpose, readiness has the separate purpose, and startup has the separate purpose. Let's understand this by real life example in production. How liveliness and readiness probe works in real front end service, checkout service, inventory service, web app, payment service, and stock service. Liveliness probe checks, is the container still healthy enough to keep running? For example, if checkout service gets stuck in infinite loop and doesn't respond, if liveliness fails, Kubernetes kills and restart the container. Readiness probe checks, is this container ready to receive traffic? For example, if inventory DB is down temporarily, if readiness fails, pod is removed from the service endpoint, traffic stops, but container keeps running. Startup probe example, when the app starts, it needs time to load product catalog, cache, and config. Startup probe disables liveliness and readiness until it passes, prevent premature restart. How it impacts in real life, user places an order, front end calls the checkout service. If healthy and ready, order gets through. If not ready, no traffic. If unhealthy, container restart. Key takeaway, liveliness is stay alive, readiness checks serves traffic, startup gives the time to restart. Question number 5, Kubernetes resource request and limits. How scheduling works and what happens on limit for each. Expected answer, provide the answer, request versus limits. What is the request? What is the limits? Minimum and maximum. What happens when limits are exceeded? CPU limits throttled by CFS quota, containers lost. Memory limit, out of memory killer kills the container, what restarts with the error OOM. Quality of services, QoS classes, guaranteed, burstable, and best. If guaranteed, request equals to limits, last to be evicted. Burstable, request is lesser than limits, evicted after the best efforts. No request, no limits, first to be evicted. In production, always set requests, set limits with care, CPU throttle, memory OA. What is the hiring manager's expectation? Candidate knows the scheduler uses the request, not the limits. Clear difference between CPU limit throttle and memory limit, out of memory kill. Understand QoS classes and eviction orders. Production mindset, set request always, limits with care. Has seen OOMKilled in real incidents and knows why. What are the common mistakes? If container exceeds its CPU limits, it's killed. It gets killed. CPU limit wrong. CPU limit throttles the container. It does not kill the container. CPU limit exceed throttled floor, container still. Correct is only memory limit violation causes the OOM kill. Memory limit exceeded, OOM killed, what restart. Key takeaways, request is equal to scheduling guarantee, CPU limits, throttle, not kill, and memory limit, OOM kill, pod restart. Let's understand this by real life scenario e-commerce system. Customer browses and place order, website, app, front end services, microservice, then database, and then payment shipping, external providers. So how it is running on Kubernetes? Front end pod, uh, CPU and memory, then product service, order service, payment service, and database. Every service has its request and limit for the resource. Why Kubernetes? Auto scale with the traffic increase, self-healing, restart failing pods, rolling updates with no downtime and efficient resource. Real life scenarios, we have seen the big billion sales. Once sales is started, traffic increases 10x suddenly. A Kubernetes HPA detects the high CPU and adds more pods. More pods are running, handles increase traffic smoothly, customer happy website stays fast and orders. Key takeaways: Kubernetes helps e-commerce systems stay reliable and available even during high traffic like big sales. This is the tech stack that we use. Follow-up questions for question number 5 and short answers. Question number 6: what is the purpose of tens and tolerations? Give the real production use case. Expected answer will be tens on node, ripple pods, formats, key is equal to value, effect. Effects: no schedule, new pods cannot be scheduled. Prefer no schedule, try to avoid. No execute, evicts existing pods. Tolerations, that is on pods. Just remember this difference. Tents on nodes, tolerations on pods. Allow pods to be scheduled on tented nodes. Node selectors, node affinities choose where to go. Tents ripple by default, toleration opts in. What are the wrong answers or common mistakes? Tents and tolerations are the same as node affinity. Wrong. Why it is wrong? Affinity attracts pods to nodes. Tents ripple pods from the nodes. You need both of precise pod placements. Affinity to attract plus tends plus tolerations to isolate. What is the expectation of hiring manager? Candidate should know all three tents effect, especially no execute, which evicts running the pod. Understands the concept tents is equal to repeal default deny. Tolerations allow opt-in, and candidate can explain with the real production scenarios: GPU nodes, spot nodes, system nodes, maintenance, and impact on the cluster management. Let's understand this by the real life example from the food delivery system on the Kubernetes. User browses restaurant and places an order. Uh, Goes internet, user access to foodie app, let's say web or mobile, and then it goes to the load balancer, distributes incoming traffic. Uh, in the different services: restaurant service, order service, delivery service, payment service, notification service. Your request goes through all these services, and eventually in the database where user order restaurants, from the cache sessions and the logs analytics. So external services can be accessed like payment gateways, maps, and the delivery partners. How it works in the diner rush hour, more user place order, traffic increases during the dinner, 7 p.m. to 10 p.m. A Kubernetes autoscales automatically adds more nodes to handle high load. Self-healing: if any pod fails, Kubernetes restarts it automatically. A smooth delivery experience, order processed without delay or downtime. Why Kubernetes? Autoscaling, self-healing, high availability, and efficient resource usage utilization. Kubernetes powers modern food delivery platforms like Foodigo to deliver fast, Zomato, Swiggy to deliver fast, reliable, and seamless experience to millions of users every day. 5 follow-up questions and their short answers. Now we go to the question number 7. That's an advanced question, and this is one of my favorite questions because fewer than 1 in 10 candidates answer it completely. Explain how Kubernetes networking works at the packet level from one pod to another pod on different nodes. Not they talk through a service at the packet level. They start with three rules that defines the whole model. One, every pods gets unique cluster-wide IP. Two, pods on any node can talk to other pods without the NAT. Three, nodes can talk to pods without the NAT. And the CNI plugin is what implements those three rules. Kubernetes itself doesn't do networking, it delegates to the CNI. Now check path. A pod A on node 1 sending to pod B on node 2. Follow it. The packet leaves pod A's network namespace. It travels through wet path, a virtual cable with one end inside the pod and another in the. It reaches the host network namespace on the node 1. There the CNI plugin routes or encapsulates it towards the pod B's IP. It creates the network overlay or plain routing to node 2. On node 2's host, it arrives and is decapsulated. If it was an overlay, then through the web pair on that side into pod. That's a full journey pod namespace with host, CNI, wire, host, with how the middle actually happens depend on your CNI. Flannel with VXLAN wraps the packet in UDP tunnel, ships it to the node 2 and unwraps it anywhere but adds overhead and shrinks your MTU. Calico with BGP uses the native layer 3 routing. No overlay routes at L3 more efficient, but it needs network fabric that supports it. And Cilium with eBPA does routing and security in the kernel data path, high performance and L7 visibility. Now, where do service fits? Only when you go through the cluster IP, then the path is pod A, service cluster IP, proxy via IP tables or IPVS, DNS that virtual IP to the real backend pod. And from there, it's exact pod to pod path we just traced. The service is just DNAT step bolted into the, which is why the killer mistake is saying pod communicates through the service. For direct pod to pod traffic, services are not involved at all. Services exist for stable VIP based app, a fixed front door to changing set of pods. But pod to pod is direct. If you can explain all three layers, the pod, network, the CNI, and the service DNAT, you are answering an architecture level. Hiring managers' expectation. Understanding the three Kubernetes networking rule, explain packet path with with pair host namespace and routing. No CNI options. VX LAN Flannel versus BGP Calico versus eBPF Cilium. Understand service flow, IP tables, IPVS, DNAT. Let's understand this by online booking platform on Kubernetes. Traveler searches flights, hotels, packages, and books the trip. It goes to the internet via web or mobile app. Load balancer distributes incoming traffic. Your services, search service, hotel service, flight service, booking service, payment service, notification service, routes through the traffic. It goes to the database and basically the external service. How it works. More travelers search service and books the flights. Traffic increases during the holidays and offers Kubernetes autoscales, uh, adds the more pods to handle the high demand, self healing, and smooth booking experience. Same, why Kubernetes uh, is required? Auto scaling, high availability, self healing, and efficient resource usage. Real business impact. Faster bookings, higher conversation, cost optimization, and better user experience. Kubernetes helps travel platforms like Tripness stay fast, reliable, and available during peak travel responses. This is similar like what we have seen last example for the food delivery app. Follow-up questions, 5 follow-up questions and short answers. Question number 8 is design question, advanced question, and it's one of that reveals whether you are actually run a platform or just use one. How do you design a multi-tenant Kubernetes cluster for 20 engineering teams? What isolation mechanism would you use? What is the expected answer? Frame it first with the two multi-tenancy model. Soft multi-tenancy, namespaces plus RBAC for trusted teams sharing a cluster. Hard multi-tenancy, separate clusters or VMs for untrusted tenants. For 20 internal engineering teams, the answer is soft multi-tenancy with defense in depth. One cluster, many layers of isolation. Naming the model choice upfront is what a senior does. Then lay out the layers, namespace, one per team or environment, RBAC, full access to your own namespace, read only access to others, resource quota per namespace cap on CPU, memory, PVCs, load balance. Limit range, default request and limit so nobody sneaks in the best effort pod that starves the node. Network policy, default deny everything, then allow only required traffic, and node isolation, dedicated node pools per year, enforce with 10. Above that, governance, OPA gatekeeper or Kiverno for policy as code, require labels, disallow privileged containers, enforce and image registry, allow list, cluster segmentation, separate control planes from prod versus non-prod, which shrinks your blast, and an internal developers platform, backstage or port for self-service namespace provisioning, RBAC, and quota management. So the platform team owns the IDP, and the teams never need cluster admin. What earns the checkmark knowing resource quota and limit range together? Most people name one. The pair is the tell. Mentioning network policy for east-west isolation, knowing OPA or QRNO for policy as code, understanding prod versus non-prod segmentation, and rising IDP self-service for what are the common mistakes that fails the question outright. Just use namespace with no quotas or policies. You get noisy neighbor chaos. Give the team lead cluster admin for convenience. That's a massive security and no network policies, meaning every service can talk to every other service, no isolation. Multi-tenancy is not namespace, it's isolation, governance, self-service layer. The expectation by hiring manager, candidate should know both resource quota, limit range, and how they work with. Mentioning network policies, east-west isolation, platform engineering example with the Finvista, built a scalable platform for 200 plus engineers across 18 teams on EKS. The challenge 18 product teams, 200 engineers. Shared EKS cluster needs strong isolation. Source reliable and self service platform. Our platform solution can be developers 200 plus engineers. Backstage self-service namespace provisioning. Backstage is open source framework by Spotify, where self-service provisioning can be achieved in less than 4 minutes. EKS cluster, shared multi-tenant cluster. Team namespaces, 18 teams, each one have the separate namespace and observability using the observability tools like Grafana, Prometheus. OPA for gatekeeping or policy as code, enforce the policy, validate and prevent, admit, reject request, continuous. Define Backstage can get the defined policies from the OPA. Same for the clusters as well as namespace. How we ensured isolation and governance. So you can define the resource quotas per team in prod, 20 CPUs, cores, and 80 gigs of memory. Limit range default for pods, CPUs, and memories. OPA gatekeeper policies. Resource limits mandatory on every pod. Images from internal registry only, like ECR, no containers running as root. Labels required, teams, environment, app on all the work. And network policies, default deny, allow only what is required. Key outcomes, 200 plus engineers empowered, zero cluster admin escalation in 18 months, new namespace in under 4 minutes, consistent security governance and cost control, high developer productivity. Platform impact can be like. So see, you have to design like this. What I design usually, and present this in your interview. Follow-up questions, 5 follow-up questions. It's short answers and the key takeaway. Now the scenario questions where I stop asking definitions and drop you into live fire. Question 9, a critical deployment update was just pushed within 2 minutes. The error rate in production spikes to 40%. Walk me through your response. And I'm watching your instinct here because your first move tells me everything. Here is the sequence. What I want to hear as a hiring manager. Step 1, rollback immediately. Contain first. Do not start investigating while users are getting error. The new version is bad. Get it out. Step 2, watch and verify. Confirm the rollout completes and error rate actually drops. Don't assume rollback worked. Was it work? Step 3, communicate. Open the incident channel, notify on call, assign an incident command. Step 4, now investigate. After service is restored, describe the failed pods to see crashed containers logs. Check metrics and traces and reproduce in staging with the bad image. Step 5, postmortem within 48 hours. Blameless, timeline, root cause, MTTR, and action items to stop it recurring. The order is whole answer. Contain, then communicate, then investigate. The classic failure, and it's the wrong answer that sinks the people, is the first I would investigate to find the root cause and then roll back. No, that prioritize your curiosity over your users and it inflates downtime and MTTR every second you spend reading logs while the site overtrap, making random changes, restart, scaling, config fix without understanding anything which can make it work, handling it silently in isolation, which delays everything and breeds confusion, and skipping the RCA, which guarantees it happens again. What I'm scoring is MTTR mindset. Restore service as top priority, the right order under pressure, fluency with the actual Kubernetes command, real incident discipline, and blameless learning culture. Rollback first, contain, communicate, investigate, learn. So you have to provide the actual MTTR in your current environment, current systems where you are working with. That gives the more trust, more confidence to the interviewer. Production incident response in action, like Zeta Global restored service in 17 minutes. New deployment caused error rate to spike 40% in just 2 minutes, impacting millions of marketing campaigns and customer data flows. High business impacts during peak hours, SLO at risk across the multiple regions. Okay, so our response timeline, so where detect, rollback immediately, verify recovery, communicate, and investigate, service restored, post. Results 17 minutes, that's a MTTR. 99.98% is availability maintained after the quick recovery. Millions of campaign and data flows protect. Zero data loss or customer impact. Rollback first, investigate later. Our priority is always our customer. Key takeaways, obviously. rollback, verify, communicate, investigate, and post. Follow-up questions and their short answers. Final question, question 10, and it's the one that separates people who have been paged at 3 a.m. from the people who have. A node shows not ready in kubectl get node. Walk me through your investigation step by step. The word systematic is doing a lot of work here. I want a method, not guess. What can be the expected answer? Here is the layered approach in order. Step 1, kubectl describe node. Read the condition, ready disk pressure, memory pressure, PID pressure, network availability, and check the last heartbeat time. Start from cluster own view, not the node. Step 2, check the node's event. Did the kubelet lose contact with the API server? Is the disk full? Is memory exhaust? Step 3, now SSH into the node and look at the kubelet. Systemctl status kubelet, and then journal control the logs last 100 lines to see why it stopped or crashed. Step 4, check system resources, whether the disk is available, memory is available, or the CPU is available, or out of memory events. Step 5, check the container runtime, because if the runtime is down, the kubelet cannot manage pods at all. Step 6, check network to the API server. Step 7, check save immediate action, drain critical pods of the node, and if it is not recoverable, terminate and replace. The order is point. Describe SSH kubelet runtime network. Check all 4 root cause families: disk, memory, kubelet, network, and show me you understand the mechanism. Not ready is triggered by heartbeat timeout. The kubelet stops reporting, and after roughly 40 seconds, the node controller marks it not. The mistakes that fails this one: SSH state in and skipping kubectl describe, that's guessing, not investigation. Rebooting immediately, which can hide the real cause forever. Deleting the node before trying to recover, more disruptions, not less. Ignoring the events and condition where the disk pressure, memory pressure is often sitting in plain sites, and assuming it's always the network without ever checking the kubelet, the runtime, or disk. Systematic beats lucky every single time. So whenever you get such scenarios, such issues, then you have to troubleshoot it throughout, not just the restarting or rebooting the node. Real life production scenario detected at 3:47 a.m. and how resolved it in 90 seconds. Incident reported at 3:47 a.m. Node status. Initial signal alerts node down for disruption. Environment production. What is the investigation timeline? So where describe the node IP, SSH into the node, check container runtime, immediate action, terminate the node replaced, and ready. Root cause disk pressure is equal to container logs not rotated, so it consumes all the disk. Container failing to pull the new images. Impact: few workloads were disrupted for 4 minutes. MTTR is 90 seconds. No customer impact. SLO maintained. What can be the resolution and prevention? Configured container log rotation in containerd. Max size 100 M. Max file 3 files. Add disk usage monitoring alert at 75%. Disk pressure event never repeated. Key, key takeaways: check node conditions first. Disk pressure is often caused and unbounded logs. Automate log rotation and alerts early. Follow up questions and it's short answers. All right, questions done. Let me pull back the curtain and tell you plainly what actually gets the people rejected. These are not trick questions. Every single one of these has happened in a real interview I have. 14 of them I'll go fast because I want you to feel the pattern. You get rejected when you can't name etcd stores. When you say kubectl delete pod to fix the crash loop back off, deleting the symptoms, not the root cause. When you confuse a readiness prop failure with the container restart, when you can't explain what happens when kubectl apply runs, yeah, the hook. When you equate base 64 encoding with the encryption for secrets, when you don't know the deployment versus StatefulSets PVC behavior, when you can't explain service endpoints, you get rejected when your first instinct is I would restart the node. When you never once mention resource request and limits, when you can't say what happens when node dies, when you claim you manage 500 node cluster but can't explain auto scaling, when you have no knowledge of any CNI and wave it away with Kubernetes handles networking automatically, when you can't read kubectl described output, and this one matters more than people think, when you don't ask any clarifying questions and just jump straight to the solution. Look at that list honestly. Notice that almost none of it is exotic, it's fundamental, and the why behind them. So here is whole lesson in 3 lines. Know the fundamental, explain the why, not just how, be honest, show depth, and share real war story. Do that and you skip every one of these landmines. These 14s aren't trick questions, they are daily habits, daily realities. So if that's what get you rejected, what I'm actually looking for, let me give you the exact mental model I use to grade every Kubernetes candidate. 3 operator can use Kubernetes, deploys application, debugs pods, writes. Administrator can manage Kubernetes, upgrade clusters, manages RBAC, configures the networking, and architect can design Kubernetes, multi-tenancy, security postures, DI strategies, platform engineering. Now, here is the observation that decides most interviews, and I want you to really hear it. Most candidates present themselves as architect, but they answer at operator level, and the gap. It shows up immediately in the following up questions. You can talk about designing multi-tenant platforms all the day, but the moment I ask how is network policy actually enforced or what does HCD stores, the real tier reveals itself in about 10 seconds. What makes candidate genuinely stand out at any tier? They explain what happens internally, not just commands to run. They know the failure modes, not just happy paths. They connect Kubernetes decisions to business outcomes. They have war stories, real incidents they diagnosed, fixed, and learned. And this is the mature one. They know what they don't know, and they're honest about. And the instant rejection tells again, claiming to be Kubernetes expert but not knowing what HCD does, unable to explain a service endpoint, never having seen a crash loop back off, which just mean no real production exposure and surface level answers that fall apart on the first. Here is my actual advice, and it's the most useful sentence in this whole episode. It's not about knowing everything, it's about thinking like an engineer. So be honest about your level and demonstrate depth at the level. An operator who deploys, understands operator level things will be beat a fake architect every time. Most people pitch themselves as architects but answer like operators, and follow-ups expose the gap in seconds. Be honest about your level, then show the real depth at it. That's me. So how do you actually build the kind of depth we have been talking about? Not just pass the CK, but be able to think inside the cluster at 2 a.m. moves, and I have done every one of this one break things deliberate. You have to produce the scenario in your local clusters, spin up the local cluster kind or K3D, any other orchestrator platforms you can use, deploy the real app, and then break it them on purpose. Watch what happens. Delete core DNS and see DNS fail. Fill the disk and watch disk pressures. Starve the memory and trigger an OOMKilled. Then use kubectl describe. Second, trace and understand everything. Know which component handles what. Read the source code, not just the documents. Understand the flow end to end. The way we traced the 9-step apply path. 3. Operate at scale. Real incidents are what make you good. Volunteer for on call. Ready your team's postmortem. Contribute a real cluster, not just try one. Survive an incident, learn from it, level up. 4. Understand the layer below. Kubernetes runs on Linux, so learn the Linux primitives underneath. C groups, namespace, IP tables with the file system. This is, I will create separate episode for Linux fundamentals, and you can watch that for the fundamentals. This is where it is. A strong foundation is the difference between memorizing Kubernetes and actually debugging. 5. Get certified but stay humble. The CK and CKS are genuinely useful, great hands-on practice. The time pressure builds the real skills and they prepare you for edge cases. But certificate is not proof of expertise. Be honest about your level. Honesty beats inflated claims every. 5 words to take with you: build, break, understand, operate, improve. Because real expertise is earned in production, not in exams or certifications. Let's bring it home. If you remember 4 things from this entire episode, remember: 1. Architecture. 9 steps from apply to running. Second, workload choice, production decisions. Third, networking layers, 3 layers, 3 responsibilities. And fourth, security is not optional, non negotiable in any cluster. Do your homework, answer the hook questions out loud right now without notes. 9 steps from kubectl apply to running a container. Next episode will be episode 5 on the DevSecOps, chiplet security, SaaS, dash, scanning policy as code, OPA gatekeeper, secret management, secure CI/CD pipe. Let's stay connected. Subscribe, like, comment your answers and the questions. Comment your topics, which I can create the video on and turn on the notification. Thank you.